Okay, welcome back to another video lecture for calculus, and this video is designed to support a calculus course that I'm teaching. One of the claims that has been made is that the derivative of the function e to the power x is itself. And this was provided without proof. And it's really not important that you know what the proof even is for Calculus 1, but that's the reason why I'm making this supplemental video, so that those of you that are interested in this, or those of you who will inevitably end up in, say, Calculus 2, where we study things like series, will understand where this derivation comes from. And I think the historical context is kind of cool too. So historically, the reason why e exists and the natural logarithm exists is because they were very, very interested in Italy in accounting principles. So how money behaves when you start applying interest to it. And so one of the really important expressions that they came up with by studying how money behaves under compound interest was this expression here for the true compound interest rate. So there's a version of this that we study in like a financial literacy or accounting classroom. It has a few more terms, but where all of those expressions and functions that describe annuities and bank accounts after X amount of compounding periods, what have you. Where this comes from is actually this expression, which was studied in the, I believe it was 1700s in Italy, when the bankers were particularly interested in this kind of thing. And what the number e is defined as, and I'm going to omit the limit thing here because this video is going to be published before we get into the limit unit. Again, we're doing this because a lot of this stuff was actually pretty well understood before calculus was really on a firm mathematical ground, with the introduction of the limit and then the definition and the epsilon delta proof, which is very, very confusing for a lot of students. So I'm going to kind of talk about them without really getting into the notations or anything. But the idea is if n is something really, really big, like it's basically infinite, then what this expression will tend towards is e to the power x. In other words, if I just omit the x term off of the left-hand side of this equation here, then that's like omitting the x term off of the right-hand side. So the definition of e is just this expression with the n's, pretend like the x isn't there, when you make n something really, really, really big. So that number turns out to be 2.71828128, and then it has some other decimals at the end of it, and it's non-repeating and it's non-terminating. And that particular function has some very unique features. And the features are that the area underneath that curve at any point is the same as what the derivative of that curve is at any point, which is also the same as what the value of the function is at any point. And it's particularly useful because we can even do some very difficult functions like the hyperbolic sine and cosine function, or even, I believe there are a couple for like sine and cosine in like the complex sort of realm, where we start using complex numbers that involve e to the power x and e to the power negative x. And a good majority of statistical functions are, at least the ones that we're concerned about in elementary statistical methods, are defined using e or the ln in some sort of way. So it's just kind of like the natural language of calculus, and it's the natural language of growth. And so that's why they got interested in this kind of thing. Now the problem is, if you attempt to do maybe our typical derivative procedure with this, you get into some pretty muddy identities really quickly. For example, the typical logarithm properties that we use, you get e to the power x in college algebra, your temptation here is to like take an ln of both sides to like get rid of the e portion of it and bring this exponent x down onto like the normal sort of way that we solve these using algebraic principles. And the normal logarithm properties that we use are like the power property, which says when you take a log of both sides, you can take whatever the exponent is and stick it out in front by multiplication. Or like the product property, which says that the sum of two logs in the same base is a log of a product of the two terms that are the inputs to those. Or the quotient property, which says that the difference of two logs in the same base is the same as the log of the quotient of those two inputs. And then I believe we discussed like change of base theorem, which is not particularly useful when what our goal is to keep this in base e so that we can find some kind of useful derivative for it that doesn't involve a bunch of crazy identities. And there are some kind of funny identities that exist out there that you could Google and look up for, say, how the log of a sum works. There is actually one of them out there that you could like Google, but it has all these kind of funny requirements to it, and it's not particularly useful, and what it'll do is it'll circle back on itself. So what we have to do is we have to do something pretty clever to come up with the derivative of this. What we're going to need is the binomial theorem, which there is a supplemental video on. And we are also going to need the general power rule from section 1.3. And basically, if we understand that this left-hand side is just another way of saying e to the x, as long as we pick n to be something really big, then that allows us to expand out this binomial. It's a really funny looking binomial, but it's a binomial to a power. It allows us to expand this out using our binomial theorem. So in our binomial theorem, we know that we get these choose functions. And I'm just going to do the first couple of terms because I think you'll see how muddy this gets, but it does follow the same pattern the further and further it goes. And we'll be able to come up with what is going to happen after the first 3 or 4 terms. So I'll only do like 3 or 4 of these. So the way the binomial theorem works is it takes whatever the power is as the top number of the choose function, which determines the coefficients. And we know that it runs from j equal to 0 up to whatever the n number is, whatever the power is. In our case, it's going to go from j equal to 0 up to nx. So j equal to 0 means that I is just nx. J equal to 1 means that I is nx minus 1. J equal to 2, nx minus 2 is equal to I. And then when j is equal to 3, I will be nx minus 3, and so on. So from here, we actually have all of the information that we need to do this expansion. So if you look at what the, when we were doing this in 1.2, it was x and dx were the parts of our binomial. And so I believe that it was mentioned in the binomial theorem video that like sometimes they use x and y, sometimes they use like a and b. It just kind of depends, like whatever the terms that they use are, they can be different. Doesn't have to be x and dx to do that sort of expansion. We'll just get 1 to the power of whatever I is, and we'll get 1 over n to the power of whatever j is when we start writing this out. Okay, so to begin with, we get a coefficient, which is this choose this, so nx choose nx, and we know that when they match, that coefficient is just 1, so this whole thing here is just 1. So we'll get 1 times 1 to the power nx. We'll notice that 1 to the any power is going to be 1, so I'm not even going to write the exponent there. So that's the nice first term. So the second term, in the second term, what we're going to get is nx choose nx minus 1, notice that the I index is precisely 1 less than the n on top. So we know that that's just whatever the n number on top is, that's nx. But then we have 1 to the power nx minus 1, and notice that every time we're going to write that down, it's just 1, because 1 to the any power is just 1. So then we have 1 over n to the power of j, that's 1 over n to the power 1, that has to be multiplied by this. And there is your second term, that's this guy. So in the third term, we start getting into some kind of muddy waters. And I want to show very quickly what the actual formula for the choose function is. Again, this video is for those of you that are interested in this kind of thing, so if you want to look up a more detailed explanation on the choose function, it will explain where some of these terms come from a little bit better. So if we have n choose k, then the formula for this is to take n factorial divided by k factorial divided by n minus k factorial. And what you will notice here is that when I use the I and the j notation, this k value is just I, and this n minus k value is just j. So it's like n factorial divided by I factorial divided by j factorial is what that is. So n factorial, notice that in this third term, what that is nx times every number underneath it until we get to 1. So it'll be nx times nx minus 1 times nx minus 2 times dot 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 times 3 times 2 times 1. Okay. When we do nx minus 2 factorial and we divide by it, what that's going to do is it's going to just cancel all of the terms from nx minus 2 down, because it's nx minus 2, nx minus 3, nx minus 4, dot dot dot, 3, 2, 1. So the 3, 2, 1 cancels, and then all of the terms nx minus 2 or less are canceled out of the factorial, which is going to leave us with nx times nx minus 1, and then all the nx minus 2 and below cancels. Okay. Then we have 1 to the power nx minus 2. That gives you your, that just gives you 1. And then we have 1 over n to the power 2, which is 1 over n squared. Like so. And then the last step in the choose function was that we had to also divide by whatever j factorial was, which is 2 factorial. And we're going to write that down like that. Okay. If we do the same thing, just one more time for good luck, notice that what this is going to do, this choose function, it's going to be something over 3 factorial. We know that. And it's going to be nx factorial, but we're going to cancel all of the terms from nx minus 3 down. So that means we're going to have nx, nx minus 1, and nx minus 2. So that's nx, nx minus 1, nx minus 2, and that's what the choose function gives us. Then we'll have 1 to the power nx minus 3, which we do not need to write down because it's just 1. And we also have 1 over n to the power 3, which is 1 over n to the third power. And then this keeps going, and you'll notice that what happens is you'll get the same thing with a 4 on bottom, and then you'll have 1, 2, 3, 4 parentheses there, and this will keep going forever, so we don't write all those down because there's no point in doing that. And what we get is this nice polynomial expansion here, and it's kind of crazy polynomial, but it is a polynomial, that tells us what e to the x is equal to. So like this thing here is e to the x, and when we expand it out we get this, so this is also equals to e to the x. Now there's some restrictions on this. Remember, n is something very, very big, like approaching infinity, and this polynomial never ends, it keeps going. Okay, but this is really hard to work with. It's really hard to work with because it's not very clean from the look of it. So let's try to make it a little cleaner. 1, it can just follow. Notice in this second term here, which I'll underline in this orange color, we have an n times 1 over n, which means that those things are going to cancel. That just leaves us with x. So that second term cleaned up very nicely. In this third term, we have to be kind of careful about this. Now notice that when n goes to infinity, like n is something really, really big, 1 over something huge, if you type this into your calculator, like 1 over 57 billion, and just use like a phone calculator for this, because I'm aware that like the TI calculators can do scientific notation and whatever. But if you use a phone calculator for this and you type in 1 over like 57 billion, you might even be able to trick it into just saying that it's 0. And that's because 1 over something that's massive, like so massive that like 57 billion, I said that because it's a ridiculously big number, but I'm talking about numbers that are even bigger than that. It's a fraction that's basically 0. So any of those terms that end up with an n on the bottom are going to just cancel out. Now notice here that this thing, if I distribute, it's going to give me n squared x squared minus nx, and then if I multiply the whole thing through by n squared, we'll have n squared. You'll notice that 2 n's cancel off of this guy, so we just have x squared, but 1 n cancels here, so we'll have x over n. Well, x, regardless of what it is, it's going to be a number like 1, 2, 3, 4, 5, 6, something. And so x over n, remember n is something arbitrarily huge, basically doesn't matter. It's like 0, okay? So, sorry, the computer did something that I wasn't entirely sure about, and so there's a cut in there. And that was rather wild. Anyway, we're talking about this term here, and keep in mind that when you expand out this nx minus 1 term, you distribute it through, we're going to get n squared x squared minus n times x. Then multiplying through by 1 over n squared, you get n squared x squared minus nx all over n squared. Now notice, in the left-hand side of this fraction, the n squareds cancel, but on the right-hand side, you are left with x over n because only one of the n's cancels. So we're going to have x squared, and then minus, and then the fraction x over n. But remember that n is something huge, and x is something like 1, 2, 3, 4, or 5. So when we plug in something gigantic compared to something very, very small, that term becomes effectively 0. So what we actually have is just x squared off of that top fraction. So we have that x squared, and we haven't dealt with this 2 factorial yet, so we're going to have to write down the 2 factorial as well, plus third term. Now notice here that we have the same sort of situation that happened in this term happening here. We're going to multiply out all the nx's. That's going to give us n cubed x cubed. Then we'll have some terms that are smaller. In other words, they'll have like n squareds or n's, or they'll just be a constant or something on the very, very end. But what we're dividing by is n to the third power. So the only term that matters there is the n cubed x cubed term, because the n cubed will cancel perfectly with the division by n cubed right here, which leaves us with x cubed. The rest of the terms in this expansion, we don't even care what they are, because we know that it's going to be x to some power over some number of n's, but n is sufficiently gigantic, which means those terms are all 0. So what we actually end up with here is x cubed over 3 factorial, and at this point we should see a pattern. We have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, you guessed it, x to the 4th over 4 factorial plus dot dot dot, and this goes on forever. We've now established a pattern here. Let me clean up this board and copy it up to the top here, and we will get to what the derivative actually is. So notice that this object 1 plus x squared on 2 factorial plus x cubed on 3 factorial plus x to the 4th on 4 factorial plus dot dot dot. Notice that what this is just a really big polynomial. And if you use our general power rule for finding derivatives of this thing, then this is actually going to be pretty obvious what the answer is. So derivatives with constants here, if you take a derivative of 1, you get nothing. If you take a derivative of x, you get 1. If you take a derivative of x squared, you get 2x. But notice that the 2 factorial thing, if you bring a 2 down on top and then you cancel the 2's, you just get 1 on bottom. So 2x over 2 factorial, that's 2x divided by 2. It's just x. If you do the same thing here, notice this is 3x squared over, and then the 3 factorial is 3 times 2 times 1, but the 3's cancel, which leaves you with x squared over 2 times 1, which is 2 factorial. That's just this term. So if you notice, when you take the derivative of this term, you get this term. When you take the derivative of this term, you get this term. When you take the derivative of this one, you get this one. And then when you take the derivative of this one, you get this one, and so on and so forth. So it just kind of collapses back down on itself. What we can write is that the derivative of this thing is just 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial plus dot dot dot. But this polynomial is precisely e to the x, so we found a series representation for this thing. In other words, we've expanded this out into some giant polynomial series. We made sure that we were following all of the conditions, which is that n is something arbitrarily huge, is how we got this thing. Then we took a derivative with this guy. We found that the 1 drops off, but that doesn't matter because we get a new 1, we get a new x, we get a new x squared on 2, we get a new x squared on 3 factorial, we get a new x to the 4th on 4 factorial, sorry, x cubed on 3 factorial, x to the 4th on 4 factorial. And if that keeps going forever, just infinitely, well then this is the same thing as that, which is just e to the x. In other words, the derivative of e to the x is just e to the power x.